Hi, in this video, we want to take a look at models in centered form, and then we want to look at what do we get when we add the assumption of normally distributed residuals. Okay, so we can write our linear regression model in this format, right? So I've got coefficients, so a y-intercept coefficient times each predictor variable, and then I have a randomness term right there. Or I can take the model and I can make a little bit of an adjustment. All right, so here, remember that my x variables are treated as constants. So if they're constant, then so is the sample average of those variables. So they're, if they're constant and they're known, so remember the x variables are known values for this, then I can go ahead and modify the model so that I have coefficient times variable minus mean, coefficient times variable minus mean, and go on down the line, randomness term just like before. But here I've got an alpha instead of a beta sub 0. Well, the alpha is beta sub 0 plus coefficient times sample average, coefficient times sample average, and down the line. Right? So if you take some time and you look at this, you'll realize that if I do a substitution, if I replace alpha with this term, and then I distribute my betas, I'm going to have a whole bunch of betas and sample averages cancel out. Therefore, these are equivalent models. They're the same model, but they have different presentations. So why would we want to have in this presentation? Well, first and foremost, some hypothesis tests are better suited to be looked at in this format. Here, where if I want to change my point of reference from the 0 vector, I'm changing it to the mean vector. So that might be interesting for what we're doing. And there are other insights that we can get out of this. Now, just let you know, when I'm doing a machine learning project, I do something like this, but I go ahead and I also divide by the sample standard deviation. Why do I do that? Well, what that does for me is that that makes it so that the coefficients and the t-score for the hypothesis testing on the slope equal to 0, that they're going to be more consistent with each other. And so it's easier to use the coefficient to judge if I have a significant slope. Also, an advantage of this is that since the x values will have standard deviation of 1, if I see that I have standard error for a slope much larger than the others, that's an indication that I have variance inflation factor on that coefficient. And so I would know that that variable is probably nearly collinear with other predictor variables, and I get that for free. I always, when I'm doing variable screening on regression or a machine learning project, I always standardize so I have mean 0 and standard deviation of 1. And so that it makes it easier to interpret things as I'm wading through. Then I select my variables, and then I go through and build it without altering the variables. All right, so the matrix form of the centered model is just going to be the constant vector of 1s times or adjacent to x sub c, where x sub c is really just the entries minus their column means, as I have here. Now here's a matrix formula for it. So if this is our regular x without the constants, then this gives us the formula for it. So notice that this does not have the constant columns of 1. And then my coefficients in the formula are very much the same, except instead of beta 0, I have alpha. And whenever you see me write beta sub 1 as a vector, that means I'm referring to this format where we don't have beta sub 0. We start at beta sub 1, and then there's alpha tacked on. And if I put a hat on it, it's the corresponding estimate. All right, well, if we do this, then our normal equations are very similar, but there's some difference. So let's go ahead and work through that difference. So I'm going to take J and centered x transpose times J and centered x times the estimate needs to be equal to J centered X transpose times Y, right? Our normal equations just modified for the centered values of X. Okay, well, I can distribute this transpose. I can distribute this transpose to get that. Now let's go ahead and do some matrix multiplication. So we're multiplying partition matrices. So we're familiar with this. So I see that I've got a 2 by 2 partition matrix. So remember, this is a partition matrix. All right, this is going to be one single term, but this is a vector times a matrix. This is a matrix times a vector, and this is a matrix times a matrix. All right, so this is a much bigger matrix than it looks like. This is a partition matrix. Okay, and then I'm multiplying just like we'd expect. Well, here I'm adding up 1 a whole bunch of times, right? So if I'm adding up 1 a whole bunch of times, that's just n. And then, oh, sorry, I misspoke. Let me back up. If I have j times a whole bunch of 1s and I do dot product on it, then that's going to be n times y bar. And then when I do the multiplication down here, that's going to be centered X transpose times y. Okay. So I'm looking at this, and I see that I have a partition matrix on the left, and I have a vector, and then what I'm trying to estimate is over here. So we're going to go ahead and make the assumption that our matrix, our partition matrix, is invertible, and then I'm going to go ahead and take the inverse, apply it to both sides, and now I have this formula. Okay, well, if we think about it, we have a special formula for the inverse of a 2 by 2 partition matrix, especially when we have a scalar, vector, and vector in these positions. So remember, this is, after I work this out, this is going to be one single number, and then I have a vector times a matrix, so that's a vector, and here this is a matrix times a vector, so that will also be a vector, but this will be a regular column vector. This will be a row vector. Okay, so we have a formula for this, and on the inverse, it's going to work out that I'm going to get 0 and 0 up here, and I'm just going to get the inverse in this position, the inverse of centered X transpose times centered X, and then this stays the same. Now I can just go ahead and do the multiplication. All right, there is an error because that should just be a y bar. Okay, well, made a mistake. Drop the n. Drop it like it's hot. All right, so then I'm going to multiply this inverse by centered X transpose times Y. And hey, that looks really familiar to us. That looks like our normal equation from regular old X. All right, we're feeling comfortable with this. All right, so we get in this situation that alpha hat is just Y bar, and beta 1 hat is our normal equation, but on centered X. Isn't that nice? Isn't that familiar? That feels comfortable to me. I feel safe and warm. All right, so if I think about alpha, I think about beta sub 0 hat. All right, I realize that all I have to do is just do some distributing, doing some, move things out, do a little bit of college algebra, and I'll end up getting, so if I have alpha hat, I can figure out what beta 0 hat is, and vice versa, as long as I know the rest of these terms of the sample averages and the estimated slopes. Okay, so if I get this going, all the centered form business going on, I can use this matrix formula to figure out what would be the y-intercept for us, which is nice. And so ultimately, the model that we're going to be working with as statisticians is going to be modeled y is equal to estimated alpha, estimated beta 1 slope times x minus x bar, keep going down the line, estimated slope of beta sub k, and then x sub k minus x bar sub k. All right, now you'll notice that the slope stays the same regardless. And that should be intuitively obvious if you think about multiplication and addition, subtraction business, that the slope is the same regardless. That's a very nice property. If we're doing something a little bit more exotic, that would not be the case. But since we're doing linear regression, it does not matter where my point of reference is, the slope stays the same. All right, now, a corollary of this is that for every single linear regression model, the model will pass through the sample average of the predictors and the sample average of the y. And so this point is always on our model, regardless of how many predictor variables we have, what our y is, what our x is. If I'm doing simple linear regression or multiple linear regression, the model always passes through the point of sample averages, which is something nice to know. So since it always passes through that point, that makes this, you know, a conceptually nice reference point for our model instead of going with, you know, the zero vector. Okay, well, the sum of squares error, we need to think about sum of squares error, right? Because that's one of the ways that we evaluate, do I have a good model? Okay, so if I go through and I take y minus y bar and I square it, so the sum of square deviations of y from the sample mean, and I subtract off beta 1 hat and then centered x transpose y, this is in fact the same as y transpose times y minus our familiar beta hat transpose x transpose y. So it doesn't matter which version we have, we're going to get the same sum of squares error. That's nice to know. All right, so now let's talk about sample variance. Sample variance and sample covariance. Okay, well, what we're going to do the most natural thing you could do if I want a sample variance matrix and covariance. Then what I'm going to do on the diagonals, I'm going to put the sample variance, and on the off diagonals, I put the sample covariance. I know you're shocked. It's amazing. All right, so on the diagonal, I have the sample variance of the predictors, and then on the off diagonals, I have the sample covariance. Now, in this version, in this presentation, we're dividing by n minus 1. So some estimates will divide by n. You know, this is going to be an unbiased estimator, but if you want to do some, you know, a different estimator, I mean, conceptually, it's not going to be that different in real life. Like if you want to do proofs and hypothesis testing, really just go with the one that's easiest. In real life, go with the one that your boss will accept or the one that you feel most comfortable with. And so keep in mind that in this situation, the predictor variables are treated as fixed constants. These are known values. So these are not estimating population parameters because there isn't a hidden population to be estimating because these are known values. Now I can write the sample variance covariance matrix in this format. And if I want S of yx, I can write in this manner also. And then we can go through, and beta 1 hat is equal to alpha minus beta 1 hat transpose x bar, which is equal to y bar minus the covariance between y and x transpose inverse on the covariance of x matrix times x bar. Okay, now for now, we're not going to deal with this. We're not going to think about, we're not going to worry about it. But down the road, we're going to return to this and we're going to take a good hard look at using this in our model when we treat x as random variables instead of fixed constants. So one of the big things about like this point of view on linear regression is that we're treating all of the predictor variables as fixed known constants. And then once we get down the road a bit, once we get comfortable and we understand everything that falls out of that, then we're going to take out that assumption, and then we're going to take a look at what happens if x is a random variable. It's going to be super exciting. It's going to be juicy. All right. For this next part, we want to take a look at the normal model. So far, we have not said anything about the distribution of our residuals except for, you know, things like expected value, variance, and covariance. So remember, expected value of the residuals is 0. The variance of the residuals is constant with respect to the predictor variables, and we have 0 covariance. All right, those are our 3 big assumptions. Okay, and the other assumption is that the model is correct. Kind of an important one. That one gets glossed over all the time. All right, so if y is normally distributed with expected value x beta, and then sigma squared times I. So here, I'm saying that if I know the x value, I know the expected value of y, and I'm saying that the y's are have constant variance and zero covariance between them. Well, the same, so if I think about my model, well, then the residuals will have expected value 0, and will have constant variance with respect to the x and zero covariance. Okay, so now I've made the assumption that we have normally distributed residuals. If I have normally distributed residuals, if I think about the work we did with moment generating functions, normality and zero covariance means that we have independence between our observations. So it's not just zero covariance, it's independence between observations. This is a big deal. You should get excited. If you aren't excited, you don't understand what's going on. I'm totally pumped for this. All right, so what do we want to do? Well, once I have a distribution, I can do something like, I can do hypothesis testing first and foremost. All right, so remember that if I want to do a hypothesis test, I'm going to need a p-value. How do I get a p-value? First, I get a distribution that is assumed to be correct. If I don't have a distribution, I can't do hypothesis testing, right? Now, there's other ways to get around that with non-parametric statistics, but there you're just kind of using a surrogate. If I want an honest to true p-value, I need the distribution. All right, so now, what else can I do? I can also do maximum likelihood estimates. All right, so if you think about maximum likelihood, what we do, we take our data, we leave the parameters, we treat them as unknown variables, we treat our data as known. We plug our data into the multivariate distribution, and then we optimize on those parameter values. That's how we get maximum likelihood estimate. All right, so if I'm optimizing, I'm making it as big as possible. I'm maximizing, and I'm maximizing the likelihood, then the value I get, I'm going to use as an estimate. That means that is my maximum likelihood estimate. It's kind of funny how the words just kind of like explicitly tell you what they do. All right, so here's my game plan. I want to estimate beta and sigma squared with a maximum likelihood estimate. All right, so I'm going to take the density. I'm going to make the density into a likelihood instead of a density. So in that situation, I treat the variables as unknowns and the data as constants. I'm going to maximize on the unknown variables, which are the parameters, and whatever gives me the maximum, that's what I'm going to use for the estimate. Now, with very little mathematical analysis, with very little advanced calculus, you know, like the Rudin textbook or measure theory, we can work out that it's going to, if we use like dominated convergence theorem or monotone convergence theorem, that the maximum will exist. Therefore, it makes sense to do this. So if this was a heavy lifting, you know, proof-based class, first thing we would have to do is show that this maximum is actually, it actually exists. That first we would take the limb soup and do stuff like that. Then we would apply dominated convergence theorem. But you know what? The maximum exists, so we're just going to go with it. We're going to run with it, and that's okay. All right, so what I'm going to do, I want to find beta hat and sigma squared hat so that when I plug it into the likelihood function, that's equal to the maximum possible likelihood value I can get for beta and sigma squared. Now, something that's important about this that I omitted to write is that this is given the data. This should be L of beta sigma squared given the data. This should be L beta hat sigma squared hat given the data. Okay. Because those are known constants. Those are given values. All right, so I want to maximize. I want to optimize. Well, how do we do that? Well, since we've been doing this since what, like high school, we've been taking derivatives, right? We take a derivative, we set it equal to 0, and then we take a second derivative, and we set it equal to 0 to, or we check to see if it's positive or negative, and it tells us if it's the maximum or minimum, and we go through that. Okay, so that's what we want to do. Now for us, we're not going to do the second derivative stuff because it works out from the structure of the problem that we can intuitively just tell it's going to be a maximum because of the nature of the function. All right, so to make differentiation, I'm not going to work with the likelihood function. I'm going to work with the natural log of the function. Okay, so logarithms are strictly increasing differentiable functions. They are strictly increasing. That means if I find the maximum after taking a logarithm, that same value will be the maximum value without the logarithm. So by solving it in an easier format, I get the answer I want. And this is why we do the log transform on this. So the logarithm is strictly increasing. Since it is strictly increasing, finding the maximum of the log of the likelihood is equivalent to finding the maximum of the likelihood, period. There's some emergency vehicles going on the other side of the lake. If you can hear that, that's on the far side of my lake. It is distracting me. Okay, so if y is normally distributed as expected value x beta, and we have sigma squared of constant variance and 0 covariance, x is n by k plus 1, and we have more rows than we have columns. So here we're saying that we have strictly more rows than columns, and x is full rank, then the maximum likelihood estimate of beta and sigma squared, well, hey, that looks really familiar, right? And then my maximum likelihood estimate of sigma squared hat is almost the same. It's just, you notice I'm not subtracting anything from the denominator. So in s squared, it's n minus k minus 1 on the bottom. Here we just have n. Okay, so I think you can actually weaken this a little bit, this assumption, so that you get a permit equality, but we're going to just go ahead and assume that we have more rows than columns for this, just to kind of like make it a little bit easier to work with. All right, so I'm doing maximum likelihood estimate. That means I take the density and I treat the data as a constant. I treat the parameters as variables. Okay, so once I do that, I take the density and basically I switch the role of the data and the parameters. So now, so I'm taking the data as being known. So then I've got beta and sigma squared. All right, now I just write this out. It's literally the same equation, but the letters have different roles in there. The x, the y, the sigma squared, and the beta have different roles than they do normally. Okay, so here is it. We're in the same format. Not the same format, but a different format. It's a little bit easier to work with. Now, what I'm going to do, I'm going to take a log of this equation. By taking log of this equation, a lot of things will cancel out. Remember, if I take logarithm of a fraction with 1 up top, that becomes negative log of the denominator. And then if I take, and multiplication becomes addition under logarithms. So I'm going to end up getting addition splitting right here. And then e is the inverse of logarithms, right? So this e business cancels out. All right, now why do I like this? Because now I've got a bunch of terms by themselves. I could brute force this, and I could do it, without the logarithm, and I would get the right answer. But you know what? I'm lazy. I want to do this the easiest way possible. Okay, so now I've gotten to this point. Here is the log of the likelihood function. And, I'm looking at this. I'll go ahead and just distribute this business, give this out to be a little bit in different format. All right, so depending on which problem I'm going to be working on, I'm going to use one of these two presentations. Now, what I need to do, I need to take the derivative with respect to beta. When I take the derivative with respect to beta, I'm going to use this lower format because you can see that I've got all the beta business expanded out and dealt with. Since I've got all the beta business taken care of in this version, when I go through and take a derivative on beta, remember I'm taking the derivative on beta for this so I can maximize the slope estimates. that's a constant because there's no beta, so it's gone. And then here, that is a constant because there's no beta in there, so that's gone. Well, when I distribute the 2 and sigma squared, I can see that there's no beta in there, so that's gone because that's going to be equal to 0 when I take the derivative. Here, oh, that now finally I got something that's not disappearing on me. When I take the derivative, it's just going to be the nice, beautiful 2x transpose y, very natural. And when I take the derivative on this part, remember I'm going to have to take a derivative like on the left and take a derivative of the right part. And when I work out all the details, I work out what's going to be happening. I'm going to have 2x transpose x times beta. Okay, so now remember, I'm taking a derivative and I'm setting it equal to 0. So I've taken the derivative at this point. I'm going to set it equal to 0. Well, if it's equal to 0, that is just a constant, right? If it's just a constant, I'm not going to worry about it because, you know, the only way I can get 0 is if the parentheses is equal to 0 when I know that this is not 0. Now, the 2's, I can factor out the 2's. I don't have to worry about it. This is just coming together so beautifully, so beautifully. So I know that inside the parenthesis has to be equal to the 0 vector. Okay, well, what I can do, I can add x transpose y to both sides, and then I hit both sides with the inverse of x transpose x. Boom, I've got it. And we go, hey, I recognize that. I recognize that. That's our estimate from before. So our maximum likelihood estimate and our least squares estimate of the slopes is exactly the same. Isn't that nice? It's blue. All right, so now let's do the same, but this time we're doing it on our estimate of the variance. Remember, this is the constant variance on the residuals, and the residuals have constant variance with respect to x. Okay, well, I'm going to go through. On this one, I want to take this presentation of log likelihood because this part we really don't care that much about. I mean, we care about it, but I mean, it's like the cousin we really don't want to interact with at Thanksgiving. All right, so I want to take the derivative with respect to sigma squared. Okay, now here's something that some people have understandably have trouble with. Here I'm taking the derivative with respect to sigma squared. I'm not taking the derivative with respect to sigma. I'm taking the derivative with respect to sigma squared. So slap a parenthesis about that and think in your mind, I'm taking a derivative with respect to the entire variance. Okay, so when I do that, that's a constant, it's gone. Here, derivative of logarithm is just 1 over the variable, right? And then here I've got the variable on the bottom of a fraction, and this is just a constant for this purpose. So I end up getting all this beautiful stuff right here. Okay, so now what I'm going to do, I'm going to set the right-hand side equal to 0. All right, so that means that all this stuff is equal to 0. So this is equal to 0. So I move this over to one side. I multiply both sides by sigma squared, and divide both sides by n, and I get my estimate of sigma squared is equal to this. All right, this is very close to our unbiased estimate. Our unbiased estimate would have a denominator of n minus k minus 1. Here we're just dividing by n. So our maximum likelihood estimate of the variance and our unbiased estimate of the unbiased estimate of the variance are slightly different. They're very close, but they have different denominators. Okay, so if I look at this, I think about it for a moment, this tells me that the maximum likelihood estimator will be biased and it will be overall on average smaller than, I shouldn't say on average, but the expected value will be less than the true value that is attempting to estimate. So this estimate of the variance has an expected value less than the expected value that it's trying to estimate. All right, so now let's go ahead and take a look at the properties of the maximum likelihood estimates. All right, so remember, when I do this, I am assuming that we have normally distributed residuals. If I don't have normally distributed residuals, I don't have a distribution, therefore I don't have a likelihood, therefore I do not have a maximum likelihood, right? Okay, so here's my theorem, theorem 7.6b. If y is normally distributed, expected value x beta, and we have sigma squared times I as our covariance matrix, x is n times k plus 1, and we have strictly more rows and columns, and we have full rank on x, then first and foremost, our maximum likelihood estimate is normally distributed with expected value of what we want. And then we have sigma squared times x transpose x inverse. That is not surprising. We already knew this part. We have that our maximum likelihood estimate of the variance divided by the actual parameter value times n is chi-squared distributed n minus k minus 1. And it works out that if I take s squared divided by the value it's trying to approximate times n minus k minus 1, that is going to be chi-squared distributed with n minus k minus 1 degrees of freedom. But wait, there's more. All right, so the slope estimates and our variance estimates will be independent of each other. Now, the variance estimates are, these two are not going to be independent of each other because they have the same numerators, but it's very reassuring to know that our slopes and our variance estimates are independent. All right, so let's go ahead and go through the proof. Beta hat is just equal to this. We already worked that out. All right, so what I'm going to do, I'm going to go ahead and take this constant matrix. So remember, X is a constant known matrix in this situation. Therefore, if I say this is A is a known matrix. Well, beta hat is equal to A times Y. Well, once I say that beta hat is A times Y and Y is normally distributed, then automatically I know that beta hat will be normally distributed, and we have A times the expected value of Y, A times covariance of Y, A transpose. Okay, so this is a theorem that we looked at previously. Well, what do I do now? I just run through and I just plug in what I want. So I replace A with what we said A is equal to. Boom, we get that. The expected value of Y, well, the expected value of Y is X times beta, right? So X times beta is expected value of Y. Now here, A is equal to this, so I slap that here. A transpose is a transpose on this. So remember, the transpose switches the order. So I'm going to get X and then the transpose of this inverse. But this inverse is symmetric because X transpose X is symmetric. Okay, so now as I'm looking at this, scalars factor out, and the identity, the identity doesn't do anything. So I have X transpose X inverse X transpose X. X transpose X inverse times X transpose X cancels out. What's left? Sigma squared and then X transpose X inverse. Boom, we got it. All right, so now to get the part 2 and part 3 of the formulas, all we have to do is write these in matrix formula, and then we apply the corollaries. And I didn't do it here because I'm lazy. I should have done it, but I wanted to get this video out, so I kind of just skipped it, just so I could get this to you hopefully in a timely manner. All right, so something that is important for us is the idea of a sufficient statistic. So it works out that our maximum likelihood estimates are sufficient statistics. So how do we prove this? Well, we prove that we can factor out the density, we can factor out the terms, and we can break it up so that the estimates are separate from each other. And that will tell us that they are jointly sufficient. All right, so if Y is normally distributed with X beta as the expected value and sigma squared times I as the covariance, then beta hat and sigma squared hat are sufficient statistics for beta and sigma squared. All right, so how do we prove this? I'm dealing with sufficiency. So all I have to do is take the density and factor out the estimated values. Once I factor out the estimated values, then I've got it. Okay, so Now to make this a little bit easier, what I'm going to do, I'm going to write y minus x beta transpose y minus x beta. I'm going to need to get a beta hat floating around in my formula, in my density. Otherwise, I can't factor out a beta hat, right? And I'm going to need to somehow get a sigma squared in there, or I won't be able to factor it out. So what am I going to do? Inside here, I'm going to add and subtract x beta hat. All right, adding and subtract something is just adding 0, right? Adding 0 does nothing. I'm subtracting and adding the same thing, same as adding 0. I haven't changed anything. All right, so now what I'm going to do, I'm going to take this part, I'm going to take this part, and I'm just going to factor it in the very natural way. So this, I put a parenthesis around. Here, I factor out the x off of these terms. And I do exactly the same thing over here. Okay, so now what am I going to do? I'm going to go ahead and distribute the transpose, and then I distribute these two terms in here with these two terms in here. I'm going to go ahead and distribute everything. Okay, so I'm going to take this, multiply by that, that gives me this part. I take this and multiply by that, that gives me this part. I'm going to take this part after I apply the transpose. I'm going to multiply it here, which gives me that part. And I'm going to take this part here and multiply by that. And remember, I do have a transpose on these guys in here, and that gives me this. Okay, so now, remember that x transpose x beta hat is equal to x transpose y. That's like how we, it's part of the derivation of beta hat. Because of that, this part, when I go through and I distribute, the x is going to be equal to 0. Yeah, and so I'm going to end up getting 0 on this. Yeah, so this cancels out, this cancels out, and I'm left with this business left. Okay, so remember, this is part of the exponent in the density. All right, now when I get to here, I look at that and I go, hey, that looks like a maximum likelihood estimator of the constant variance. Boom, right there, except for I've got the n in there because here I don't have any division going on. And then this, I'm just going to leave alone. All right, so now I've worked out that this part is equal to this. So what I can do, I can take this part of the density and just slap this in for it. And boom, I've got this part in the density. Now, what I have to do, I have to factor this density. So I have addition inside an exponent, right? Addition inside an exponent converts to multiplication, which is what we want. All right, so I know that this part with the 2 over sigma squared comes out here. This part with the 2 over sigma squared, with 2 with sigma squared, is this part here. All right, now I take a look. I look at this, and I see that with respect to sigma hat squared and beta hat, that's a constant. So really, we don't care about this for the purpose of sufficient statistics. I look at this part, I notice I don't have a beta hat. I look here, I notice I don't have a sigma squared hat. That means I just factored it in the way I wanted. Since the distribution, since the density factors with respect to the estimates so that they're separated in the factorization, I know that each of these are going to be sufficient statistics. Now, something that is important to notice is that, all right, here I don't have any betas going on, right? But when I look over here, I've got sigma squared. Because of the sigma squared is in the beta hat part, that means that these are not these are not independently sufficient. So if I was able to factor out the estimate and the parameter, then I would have independent sufficiency. But here I don't. They are jointly sufficient. That means that if I want to have sufficiency, I have to be taking them together. Now, if I want, I can naturally extend this to s squared just by rescaling sigma squared hat. All right, now, theorem 7.6d, if y is normally distributed with the expected value of what we want, constant variance, and 0 covariance, then beta hat and S squared have minimum variance of all unbiased estimators. So this is a big whoop-de-doo. All right, so if I go ahead and I add on the normal assumption, not only do I have minimum variance of all linear estimates for beta hat, not only do I have minimum variance of all quadratic estimates for S squared, I have minimum variance of all unbiased estimators, every single one. All right, so without normality, beta hat would be minimum variance of all linear unbiased estimates. Without normality, S squared has minimum variance of all quadratic unbiased estimators. But if I go ahead and I add on the normality assumption, it works out that these are going to be minimum variance of all unbiased estimates. That is powerful. Now, a corollary of this is if y is normally distributed, and we have the parameters that we come to know and love, then for any constant vector A transpose beta hat is minimum variance unbiased unbiased estimator of A transpose beta. All right, that's all I've got for you. Take care and goodbye.